Okay, right, I think we were going to now move to another example. So we're going to be looking at 4-amino benzoic acid.
Oh yes, picture here. Yep.
So shall I remove those?
Okay, that's good. Lots of bits of paper. So here is the structure of 4-amino benzoic acid. Okay, and we're going to look first of all at the number of environments.
I think so.
Okay, so let's do that. So we've got, the reason we're looking at this partly is it's got some particular protons of interest. So actually, particularly the NH2 and the carboxylic acid groups. They're quite different ones than we've looked at previously. So let's just first of all count the environments. So let's just have another pen. So that's hopefully clearly one environment. Okay, the NH2s are one environment. It's a bit like the one we did before. That's a second environment. A third environment. There's obviously no hydrogen here or no hydrogen here. And then finally, there's a fourth environment. So we'd expect to see 4 signals or 4 resonances in the hydrogen NMR for that molecule.
And I think in this case we really would expect to see the aromatics looking quite different here because they are adjacent to such different groups. So you would expect to see kind of clearly defined peaks, I would hope, in the spectrum.
Yep.
Okay, so are we going to get up? We're going to get up the spectrum quickly and then
spectrum just to make sure that what our prediction is what we expect, and yes, it is. So again, we've seen 4 signals. 1, 2, 3, 4 signals, which is great. And the next thing we're going to do is have a look at what those signals might be.
So in this case, we're looking at the correlation chart for protons attached to heteroatoms, okay? Because obviously we're looking at the carboxylic acid proton and also the amine proton. So if we look at the carboxylic acid, we would expect that to be around 10 to 13 parts per million, so very, very high. It's very heavily de-shielded. So we have a peak here around about 12, so that is likely to be due to the proton on the carboxylic acid. And for an amine, and you can see it's split, hopefully you can see this on your own correlation chart if you can't see it here, but for aromatic would be between 3 to 6 parts per million. So it is likely to be
that one.
This peak here.
This peak here, yeah.
And these two are the aromatic peaks.
And you can see there's quite a wide separation in this case, as Ellen has just said, because they're quite different types of aromatic peaks, so we don't see that overlapping feature that we saw in the ethyl benzene example. Okay?
Okay.
So, am I going to talk about the amino groups now and the
yes.
acid groups? Okay, so
we've got a break for you.
Because it's a lab cast, we should do a small amount of practical work. It's a very small amount of practical work. So one of the things that you'll have learned, hopefully seen in the module materials, and there's more about that in those, is that you can do so-called D2O shake to identify the presence of so-called exchangeable protons. So those like in an NH2, and also those in a carboxylic acid group. Okay. So what all we'll do is just demonstrate how you would do a D2O shake, and then we'll just look at the spectrum. So let me just get up and do that. So I'm going to have to put a lab coat on. So I think they're going to, and some glasses. It's probably overkill, but okay. So I have an NMR tube here of the 4-amino benzoic acid, dissolved in actually DMSO, which is the deuterated solvent we use to run these spectra. And all I'm going to do is add a small amount of D2O to that sample. So we've got some D2O in this bottle here. I'm just going to add a small amount. And so what we have done is normally just run this sample originally, then obtain the spectrum there, and then add some D2O and just see the effect. So let me just take off the lid and open up my D2O. And all I have to do literally is add a few drops. It's a really easy experiment. Take a pipette and then literally add a bit in, like that. And then stick that back in there, put the cap on, back on, and then literally recap it, and just give it a little shake. And then all we would do is run the spectrum resulting from that. Okay, so that's literally how you do a D2O shake. So let's just then go back and have a look at the effect of that D2O shake. So we've rerun the sample, and then have a look at the effect of it. So I'll leave my coat on and bring the spectra across. Okay, so let's have a look at the spectra from that. So we've got, at the bottom here, we've got the previous spectrum that you've already seen, and I've drawn on again the structure of 4-amino benzoic acid. And we see our 4 signals. The one above it is the spectrum we obtain when we add the D2O, and hopefully, as you can see, the peak at 12-ish, which was the carboxylic acid, gone. The peak at 5.8ish, the amino group also gone. And what's happened here literally is that the deuteriums in the D2O have exchanged with the protons in both the NH2 and the carboxylic acid group. So this is no longer NH2, it's actually ND2, so we don't see it. This is no longer OH, it's OD, so we don't see it. So we don't see signals due to these exchangeable protons. We do see an additional signal, this one here, which is at around 4 ppm. That's not actually due to the compound, not actually due to this molecule. It's due to the fact we've added some additional D2O, and D2O always contains a small amount of HOD or even H2O. So we see the signal due to those protons when we add our D2O. It's an artifact rather than anything to do with the sample.
And there's a small animation of that. So if you go into the interpreting proton NMR unit, so I think one of the sections there has a little animation that kind of shows you about that exchange that you see.
Yeah.
Okay.
Okay.